Bismillahirrahmanirrahim. Hello, dear students. I hope you are having a nice day. I welcome you all to the class of real analysis. In today's lecture, we will discuss the solution of first five question of exercise. The first question is this is very important question regarding your final exam. In this question, we have to prove if R is a rational number and X is an irrational number, then their sum R plus X or their product Rx both are irrational numbers. To prove the sum and the product are irrational, we suppose on the contrary that R plus X is uh, is equal to some rational number P, that is R plus X is equal to P. Subtracting R on both sides, we have X is equal to P minus R. Say this is question number 1. The right hand side of 1 is the difference. This is the right hand side, that is P minus R. This is the difference of two rational numbers, and we know that the difference and the sum of two rational is always rational. So this difference P minus R, when P is rational and R is also rational, so this difference is also a rational. But on the right hand side, on the left hand side, the number is X, and X is irrational number. It is given X is irrational, this is given, and this is not possible that a rational number is equal to an irrational number. While on the left hand side X is an irrational number, it is not possible that a rational number is equal to an irrational number. Hence our supposition is wrong and R plus X is an irrational number. Next we show that the product Rx is an irrational number. We again suppose on the contrary that Rx is a rational number and say it is equal to Q, where Q is a rational number. As it is given that R is a non-zero rational number, so its multiplicative inverse 1 over R must exist in R. So taking 1 over R on both sides, we have 1 over R into Rx is equal to 1 over R into Q. By using the associative property, this will be cancelled, and on the left hand side we have X is equal to Q over R. As Q is a rational number and R is a rational number also, and we know that the quotient of two rational is again a rational, so this is the form of this is a rational form. But X is an irrational number, that contradict with our assumption that Rx is an irrational number. Hence Rx is an irrational number. Next we move towards question number 2. This is also important question. We have to show that there is a no rational number whose square is 12. In other words, this question can be stated as show that square root 2 is an irrational number. Is an irrational number. We will prove this. We will prove the irrationality of square root 12 by contradictory. So we suppose on the contrary that there exists a rational number R such that whose square is 12, and let R is equal to P over Q, where where R is in its least form. In other words, the GCD, these two brackets shows the GCD of PQ. This shows GCD, greatest common divisor of P and Q is 1, which means there is no common factor between P and Q other than 1, and further the denominator Q is non-zero where P and Q are integers. Substitute this value of R equal to P over Q in question number 1. We have P over Q whole square is equal to 12, and from here we have P square is equal to 12 times Q square. We can make the prime factorization of 12, which is 2 square into 3 into q square. Now this is important. If you notice the right hand side of 2, this contains the 2 prime factor 2 and 3. The right hand side of 2 is divisible by 3. It is also divisible by 2. It is also divisible by 6. It is also divisible by 4. You can take any divisor here. I am taking the divisibility by 3. So, as the right hand side of 2 is divisible by 3, that is 3 divides 12q square. As 12q square is equal to p square, it means 3 divides p square. In number theory, we have a result if a prime number, divides a, in a number theory, we have a result that if p is a prime and it divides the square of an integer, then this prime must divide the number itself. So here 3 is prime number that divides p square. This implies this 3 must divides p without square. It means p is a multiple of 3. So let p is equal to 3 times m. 3 times m mean multiple of 3. Substituting this value of p, that is 3m, in equation number 2 here. Substitute this value of p here. We have 9m square is equal to 12q square. When you substitute p either here or here, we get 9m square is equal to 12q square. Cancelling with 3 on both sides, we have 3m square is equal to 4q square. Now we have to find the value of q square. On the left hand side, you can see that this number is divisible by 3. This shows 3 divides. This vertical line means divides. We read it as 3 divide 3m square. It is clear that 3m square is divisible by 3. As 3m square is equal to 4q square, it means 3 divide 4q square. Again, in number theory, we have result that if a divides the product of two integer bc and the GCD of a with one of them is equal to 1, then it must be that a divides the second number c. So here you can notice that 3 and 4 have a no common factor other than 1. It means their GCD is 1. So it shows that 3 must divides q square. So if 3 divides q square and 3 is a prime number, so again using the above result, which says that if a prime number divides the square of the number, then that prime must divide the number without square. So if 3 divides q square, it means 3 divides q. This shows that q is also multiple of 3. It means the common factor between p and q is 3, which is contradiction to our assumption. Our assumption was p and q have a no common factor other than 1. So our assumption is wrong. Hence our assumption is wrong. So there is a no rational number whose square is 12, and in other words we can say that square root of 12 is an irrational number. Next, question number 3. In question number 3 we have to prove the proposition 1.15. What was the proposition 1.15? The proposition 1.15 is given below. It started from here. The axiom for multiplication imply the following statement. This proposition consists on the 4 parts. The first part is if x is non-zero, then and xy is equal to xz. If x is non-zero and we have given this equation xy is equal to xz, then we have to show that y is equal to z here. I will prove this part by using two methods. Method number 1, given that x is non-zero, this implies its multiplicative inverse 1 over x must exist in R. Given equation is xy is equal to xz. So taking the multiplicative inverse of x on both sides and by using the associative property. So when we multiply this these both sides with 1 over x, we have 1 over x into xy is equal to 1 over x into xz. Using the associative property, we can combine 1 over x with x on both sides. As x and 1 over x both are the reciprocal of each other, so their product is equal to the identity 1. As 1 is the multiplicative identity, so when you multiply 1 with y, this gives y and this gives z, which is required to prove. The second method is, for all y belong to R, we can write y is equal to 1 into y, because 1 is the multiplicative identity, so when you multiply 1 with y, there will be no change. So we can write y is equal to 1 over y. As we can replace 1 with 1 over x into x. So this implies y becomes 1 over x into y. By using associative property, we can combine x with y, so it becomes 1 over x into xy. But it is given that xy is equal to xz, so replace xy is equal to xz, and again using the multiplicative property, we have 1 over x into z. 1 over x and x both are the reciprocal, so they will be cancelled out and it gives 1, so y is equal to z. Its second part is that if x is non-zero and xy is equal to x, then we have to show that y is equal to 1. Given that x is non-zero, so its multiplicative inverse 1 over x must exist in R. Given equation is xy is equal to x. Again we multiply the multiplicative inverse of x on both sides, and using the associative property, we have 1 over x into xy is equal to 1 over x into x. By using the associative property, we can combine these two terms. So 1 over x and x gives 1, this becomes 1 into y, and this is equal to 1 over 1. That is y is equal to 1. Its C part is, if x is non-zero and xy, the product of xy is equal to 1, then y is equal to 1 over x. In other words, you can say that if the product of two numbers is equal to 1, then 1 is the reciprocal of the other. Given x is non-zero, its reciprocal 1 over x exists, such that x into 1 over x is equal to 1. It is given that xy is equal to 1, multiply on both sides by the reciprocal 1 over x, we have 1 over x into xy is equal to 1 over x into 1. By using the associative property, we can write it as 1 over x into y. 1 is the multiplicative identity, so this gives simple 1 over x. By cancelling out, we have 1 into y is equal to 1 over x. 1 is the multiplicative identity, hence y is equal to 1 over x. The last part. If x is non-zero, then we have to show that 1 over x is equal to x. By using the C part, which says that if x is non-zero and the product xy is equal to 1, then y is 1 over x, that is y, one of the number is reciprocal of the other. As we know that x into 1 over x is equal to 1, so, and also here x is non-zero, so it satisfied the above result, which says if the product is equal to 1, then 1 can be written as the reciprocal of the other. So I am writing here, by comparing star and double star, x, that is one of the number, can be written as the reciprocal of the other. So x can be written as the reciprocal of this number, 1 over x. Next, in question number 4, we have to show that if E be a non-empty subset of an ordered set, suppose alpha is a lower bound of E and beta is an upper bound of E, prove that the lower bound is always less than or equal to upper bound of E. It is given that E is non-empty, as alpha is lower bound of E. Now, what is the definition of lower bound? The lower bound is a real number if we particularly assume the field R, then alpha is a real number that is less than or equal to every element of E. If alpha is a lower bound, then it must be that alpha should be less than or equal to every element of E. So alpha is less than or equal to x. Say this is equation number 1, inequality number 1. Similarly, as beta is an upper bound of E, so by definition of upper bound, beta should be greater than or equal to every element of E. By combining 1 and 2, we have alpha is less than or equal to x, x is less than or equal to beta, or it can be written as alpha less than or equal to beta. Further, since E is a subset of an ordered set, so by the property 2 of ordering, if you see in the textbook, there is a property 2 of orderings which says that the lower bound is always less than upper bound. Lower bound is always less than upper bound. So alpha is always less than beta unless alpha is equal to x, x is equal to beta. This case is possible. Suppose our set E consists on a singleton element. Suppose this is suppose this is 1. E consists on the singleton element 1. Now, what is the least upper bound of E? Least upper bound, that is the supremum of E. This is equal to 1. And what is the infimum of E? Infimum of E is also equal to 1. So in this case, your x is equal to 1, your upper bound, your lower bound are all equal. So this is possible in this case when your set is a singleton set. Next, question number 5. This is also important question, and this is the property of supremum and infimum. Let A be a non-empty set of real numbers which is bounded below. Let minus A be the set of all real numbers minus x, where x belong to A. Prove that infimum of A is equal to minus times supremum of minus A. This property is also given in the textbook of Robert G. Bartle. In that book, this property can be stated as, the above statement is same as, but this condition can be written as supremum of A into A is equal to, if A is a negative real number, is equal to minus time, A into infimum of A. And if particularly you put here A is equal to minus 1, you can get this result of Walter Rudin. Actually, this is the general property. This property hold for any negative real number. Actually, when you put here, when you multiply the set A with any negative real number, then supremum convert into the infimum, and the vice versa. So now let us discuss our particular result. As A is a set of real number and minus A is the set of negative real number, so minus A can be defined as minus x, where x is an element of A. Given that A is non-empty, A is a subset of R, A is a bounded below, this implies A has a lower bound in R. Because you know that this is the result, any subset of real number which is non-empty and is bounded below always has a lower bound in R. This is the fundamental property of R. Since R is complete ordered field, so it must be that infimum of A must exist in R. This is the completeness property of R, which says that every non-empty subset of R which has a lower bound in R must have infimum in R. Suppose infimum of A is equal to U. It means we have to show that, now we have to show that minus times supremum of minus A is equal to U, because our required result is supremum of minus A is equal to infimum of A. But now our infimum is, we have assumed infimum of A is equal to U. It means we have to show that minus times supremum of minus A is equal to U. Or in other words, if you multiply minus on both sides, supremum of minus A is equal to minus U. What does this expression shows? What is the definition of supremum? Actually, definition of supremum is least upper bound. It means we have to show that the least upper bound of minus a is equal to minus u. Least upper bound of minus a is equal to minus u. To prove this result that minus u is the least upper bound, I will prove this result into two steps. Firstly, I will show that minus u is an upper bound of minus a. This is my first step. And what will be second step? In the second step, I will show that minus u is least upper bound of minus a. To prove the second step that minus u is the least upper bound, I will assume another upper bound of minus a that is greater than or equal to minus u. This will prove that minus u is an upper bound, but it is the least upper bound. So let us start from here. From 1, we have assumed that u is the infimum of a. If u is the infimum of a, what is the definition of infimum? The definition of infimum says that u should be less than or equal to every element of a. So u is less than or equal to x, every x. To make the form of minus u, multiply minus 1 on both sides. We have minus u greater than or equal to minus x. Now look on the left hand side, right hand side of inequality 2. Since minus x is an element of minus a, this implies minus u is an upper bound of minus a. Again, minus x is an element of minus a and it is an arbitrary element of minus a. When you say minus u is greater than or equal to every arbitrary element of minus a, what does this mean? This means that minus u is an upper bound of minus a. So it completes the first step. Minus u is an upper bound of minus a. Now I will show that minus u is the least upper bound of minus a. Now we are going to move towards second step. For this, we let v belong to R is another upper bound of minus a, and we will show that v is actually greater than or equal to minus u. Since v is another upper bound of minus a, it means by definition of upper bound, v should be greater than or equal to every element of minus a. The elements of minus a are of the form minus x. So it means all minus x are greater than or equal to, less than or equal to v. Multiply on both sides with minus, we have x greater than or equal to minus v. This shows that minus v is less than or equal to x. Again, look at the right hand side of 3. The right hand side of 3 is x, and x is the element of a. It means 3 shows that minus v is the lower bound of a, because x is an element of a and minus v is less than or equal to every element of a. It means minus v is the lower bound of a, but the lower bound of, it means minus v is the lower bound of a, but u was the infimum of a. Infimum of a mean greatest lower bound of a, and minus v is the simply lower bound of a. So it means greatest lower bound must be greater than or equal to a lower bound of a. So it means u, that is the infimum of a, that is the greatest lower bound of a, it should be greater than or equal to minus v. So u is greater than or equal to minus v, or in other words, when you multiply with minus 1, we have minus u is less than or equal to v. That is our target to show. V is greater than or equal to minus u. So minus u is less than or equal to v. What was v? V was another upper bound of minus a. So minus u is the least upper bound of minus a. Hence, supremum of minus a is equal to minus u. Supremum mean least upper bound. Who is the least upper bound? Least upper bound is minus u. So supremum of minus a is equal to minus u, or multiply minus on both sides, we have supremum of minus a is equal to u. As u is the infimum of a, so replacing u with infimum of a, we have the required result. So inshallah, in the next lecture, we will start from question number 6. I hope now you have a clear understanding of these 5 questions. Kindly, if you find these lecture helpful for you in any way, kindly like, share, and subscribe my channel. See you in the next lecture. Take care. Allah Hafiz.